mostly going to do education on that project. And that project, we can look at it for just a minute. This is what it asked. It asked for the first deployed quantum key distribution network in every state country of the EU. Okay? So every country had to answer that demand. And it states that it needs to operate with existing communication networks. Okay, it asks a few other things that I will cover much less, addressing different advanced use cases. It also aims at seeding or making the industry around quantum technologies grow in Belgium. And it wants to train users on that topic, a bit like we want to do in the field of cybersecurity. That's what we try to answer to. Okay, but I guess I should actually start by explaining that title, because you're not that familiar with quantum key distribution. You certainly already know about communication networks, but what does that mean, quantum key distribution? Well, it's aimed at answering an upcoming problem. So today we have not really talked much about the cryptography. We assume that basically this is settled. We have codes, encryptors that work. But in the not so distant future, we'll have quantum computers that will be able to crack some of those encryption machines. Not all of them, but some of them for sure. And there's an easier solution in terms of encryption. That's what's illustrated here. It's a very dumb encryption method. It's basically you have a message, you add a random key to it, you have an encrypted message that nobody can detect. Problem of that method, you need this encryption key to be as long as your message. And you need this encryption key to be only in the hands of the receiver. Okay. So all the game of quantum key distribution, why it's called quantum key distribution, is to have this key and distribute it around in a safe way. Okay. Now, in the code, it also stated existing communication networks. Well, you certainly know about telephone line, 5G, fiber networks, satellite communication. It happens that presently the only realistic option for this kind of quantum key distribution is to use a fiber network. Okay, and that will appear hopefully clear in a moment. Okay, in quantum key distribution, we like to give names to our A and B protagonists. Here is Alice and Bob, and in that specific case, Alice is the sender of the key. Alice is going to send a quantum object. What is a quantum object, you shall ask? Well, it's an object that you can only describe completely if you use a quantum theory. Okay, if you don't use a quantum theory, then you start to have problem. Don't panic, you won't need to know all the quantum theory. That object can be in two states. Very often we see this as a spin up, a spin down. You don't need to know what that is. Just remember, it can be an arrow to the bottom or an arrow to the top. One thing that is a bit peculiar about a quantum object is that it can be in two states at the same time. Okay? And that's when people may panic. Okay? We sometimes write this like this, the fact that it's at the same time pointing downwards and at the same time pointing outwards. And actually, we even write it like so. But what it means actually is fairly simple. If you have a measurement apparatus that allows only to measure something that is pointing down or something that is pointing up, but we are measuring a state that is this one, then we will be right only half the time in our measurement result. And the other half of the time will be correct. Okay, that's basically all you have to remember about this kind of superposition. If you measure with something that is capable of distinguishing downwards this state, then half the time you'll measure downwards, but the other half of the time you'll measure upwards. On the other hand, you could have measurement apparatus that is directly able to measure whether it's the plus or minus state, and you see it depends on the plus or minus here. Okay, Another thing that you need to know about this kind of state is that there are ways to transform from this to that and from that to this, etc. Now, in this quantum key distribution protocol, we'll have two ways to code a zero. To code a zero, either we have this state that is pointing upwards, or we have this kind of superposition with a plus sign. And if we want to code a one, we have either the arrow pointing downwards or this minus state, which is this one with a sign minus here. Okay. So if they want to use these states and communicate anything meaningfully, that means that Alice needs to encode information in the same set of states here as Bob is ready to receive. Okay? If Alice sends a particle that is pointing downwards and upward, and Alice is capable of measuring upwards and downwards, there is no problem. If, however, he has an instrument that is capable only to measure plus or minus, then yeah, half the time he'll have a wrong result. So I'm trying to summarizing this by an example. Let's say that Alice encodes on a horizontal vertical choice, and that she's sending something that is pointing upwards, then Bob measured using the same kind of apparatus is measuring also upwards, and they know that they have a zero. On the other hand, if Alice do the same thing, she sends something that is horizontal this time, but the measurement is made on a diagonal instrument, then he'll get an answer that is diagonal, and he cannot actually I forgot to tell you something. In that case, it does not have information. How does he know that it does not have information? Because he actually shares the choice of measurement apparatus he made. Okay? Bob shares the kind of apparatus he's used for his measurements. Okay, so what could an eavesdropper do to get the encrypted message, or not the encrypted message, but the key? Well, the eavesdropper can only do the same kind of procedure as the sender, and the sender is randomly selecting whether it encodes with this set of states or with this set of states. Okay, so it's random, so that means that the eavesdropper cannot know in advance and have to pick randomly as well. Or if it does not, it won't change. It's still random. So that means she will make mistakes half the time. And half the time, she will therefore get a wrong result. Well, half the time, so 1/4 of the time, she will get a wrong response. And from there, what can she do? Well, she can only send a similar object to Bob, so that, okay, Bob still thinks that the communication is going on, but she will make mistake. And so that means that Bob will have sometime wrong answers. So Eve induces error at Bob's end. And then from there, it's fairly easy, because what can Alice and Bob do is simply compare a fraction of the secret key and see, oh, I have mistakes there. Something is fishy. I should stop using this channel. This is no more secure. I cannot encode my message with that. Okay. So here I was summarizing the whole procedure. There is an encoding in a choice of two bases, a choice of bit that is random as well. And then Alice and Bob needs to share in what of those two bases or set of states they made the encoding, and from there they can extract the bits where they have made the same choice of basis. In practice, there are some errors that are not due to necessarily to an eavesdropper, but due to imperfection of the system. But if you want to guarantee security, you have to assume that those errors may come from an eavesdropper. Okay. And if the amount of error is consistent with what is expected, then that means there is no eavesdropper, and one can eventually use the encryption key to encode the message. And the message can be transmitted then to the public. It does not need any further encryption. So what are the tools for doing that then? Well, I told you about quantum objects, okay? And I told you about those different states. And I told you about randomness. So in practice, those quantum objects, they are most of the time single photons, okay? Because single photons, you can send them very far away, they propagate easily, and we more or less know how to make sources of single photons. Another choice is to use light, but not a single photon, but what we call squeezed states of light. And I'm not going to talk about that. It's a bit less intuitive than single photons. And then you need, as I said, two different states, two sets of two states. And one textbook choice is to use the polarization of light. So the polarization of a single photon that we know very well how to have an horizontally or vertically polarized photon, and similarly easily photons that are polarized diagonally or anti-diagonally, or even circular left, circular right. There are other degrees of freedom. I just mentioned them, but not really going further than that. So you can use the timing of your single photon as a degree of freedom. You can use the color. You can use different paths. So there are many options. But for the sake of simplicity, we'll stick with the polarization. And then you need random numbers. These are actually important. There are various ways, but as we are quantum engineers, well, we care about quantum random number generator. There are limitations, and I will not cut to that. While photons are very good at preserving their quantumness, if you wish, so preserving the states pointing up or pointing down, they are not so good as traveling without loss. And if there is loss of a single photon, you have nothing left. You have no information left. You cannot do anything. So essentially, as the distance increase, you have a rate of key generation that decreases exponentially. And just to give you some ideas, if you have 50 dB of loss, I'm not sure I'm giving you an idea to everyone here, but the rates of key transferred can be extremely low. Okay? 100 bits per second. If you want to encrypt a message and your message is 100 bits, that's not even an SMS. Huh? That's very, very small. And furthermore, as I said, there are imperfections in those devices. For instance, imperfection of the source. If you have a perfect single photon source, you have this black curve here. But if you have a source that is simply a light pulse that is attenuated down to a single photon, you have actually much more sources of error, if you wish. You also have detectors that sometimes think there's a photon while there's not. These create even stronger bonds, and they basically explain why after some amount of loss, you basically cannot even increase anymore the rate of generation of a safe key. Another limitation is the fact that there might be a side channel attack. So implicitly in what I've discussed thus far, I've supposed that Alice and Bob, the sender and the receiver, they are in safe enclaves. They are completely isolated from the rest of the world, and nobody can attack them. But of course, that's not true. That was actually most of the topic of today. And we have to account from that at some point. So we have to account for the fact that there is typically a key management system associated to a quantum key distribution system. There are cryptors, there are servers, etc. Okay. And yeah, okay. A third limitation is the connectivity. if you want to connect several people, a typical fiber network would look like this. It's simply a loop, and you can go from Alice to David simply by going to Bob and Charlie, okay, or the other way around. But the quantum key distribution, as I explained it, is a point-to-point technology. That means that's the amount of link you need. Okay, that's definitely not something very sustainable. And last but not least, limitation is the hardware. It's optics. Optics is typically not cheap technologies. They can be bulky. The first demonstrations look something like that. One important thing is typically those transmission of single photons, they don't coexist with the regular IP traffic. Okay, so you need really a dedicated fiber between two places for this to work. So it's quite strong limitation on the hardware. Okay, so when we got this task of answering to this project, we were more or less aware of those limitations, and the idea was, okay, can we address those limitations so that further deployment can be tractable in some sense? And so there are solutions to some of the problems. Some are more advanced, some are less. Just want to give you a feel of some of them. There is one that is the simplest, but that does not do so much. So for the distance problem, you can say, oh, I'm going to use an intermediate sort of repeater. Okay? Then Alice and that Charlie are basically sharing a key, and that Charlie and Bob, they are sharing another key, and then you simply do the addition of the key, you share it to the public, and from that addition of the key, both Alice can recover the key of Charlie and Bob can recover the key of Alice and Charlie, and so they can use both keys. Okay, that's perfectly legit. But what if Charlie is this guy instead? You say, maybe I'm not sure I can trust this one, or worse, definitely you cannot trust this guy. So this kind of repeater really suppose that any node at the center here must be trusted. Okay, with one node, okay, maybe you can live with that. If you need 30 of them, that becomes really a big problem. Okay, so that kind of answer is not satisfactory, yet we'll see that it is often implemented. Another bit better solution, not really dealing with the distance actually, but another thing that is quite convenient is what we call measurement device independent quantum key distribution. So here, Alice and Bob still encode information, and for simplicity, I'm assuming they use only one base, but they'll need to use both. And we are having a Charlie that has a quite different instrument. And here I need to be a bit more specific and not general. So I'll assume that the single photon is encoding the polarization degree of freedom. If he has this instrument, something a bit peculiar happens. And we are going to look at all the case possibles. Either Alice and Bob have different photons, so photons that are polarized differently. And in that case, well, if it's an horizontal photon coming here, it goes this way. If it's a vertical polarization photon, it goes this way and there. So you basically have a detection here and a detection there. I'm not going to look at all the cases, but I guess you can trust me. Then when I have one as a vertical and the other as a horizontal photon, basically you have two detections, okay, in two of the four detectors here. However, in the case where they have both the same photons, the same kind of photon, then all the photons ends up in the same detector. So you can basically distinguish those two cases. So this Charlie here is going to tell to Alice and Bob whether he has detected two photons or only one. And if it's two, then Alice knows that Bob has the other kind of photon, and Bob knows that Alice has the first kind of photons. So they do have information on each other, But this guy, he has no information. He does not know from where the photon is coming from. Okay, so we have now a Charlie that we don't need to trust, in other words. And that's convenient because one of the most common channel for attacks in quantum key distribution is actually at the measurement side. Okay, so now the measurement side does not need to be trusted anymore. Okay. By the way, this is called a Bell state measurement. Okay, so that's what just I said, no breach of security if there's a breach here. It's also well suited for star topology because you can have switches here and imagine that you have other users with this as a central node. Okay. I think I'm speaking not as fast as I thought, so I'm going to skip this one and this one. This is another way to go at a distance that is larger. It involves what we called quantum repeaters. So what you need to know about this, well, among the several limitations that we have, some of them can be sort of addressed. For instance, the topology, the measurement device independent QKD can help you with that. The security, well, thus far, it's really looking only, for the most case, at the link itself. But in the near future, the idea is to look at the whole setup and make a proper analysis of that. The cost of the hardware is also significant, and there are ways to deal with that. One is integrated photonics. Another one is to work with those squeeze states that I glanced over in one of the earlier slides. And then for the distance, there's no solution available today. So the only solution we see is to use post-quantum cryptography for longer distances. Satellite is one, but it's not really existing networks. For the day after, well, there are those quantum memories that I glanced over for the distance and for the topology. Okay, I'm coming now to this Belgian QCI, Quantum Communication Infrastructure. And basically there are two parts to it. There's a part that is really research. So looking at those tomorrow and the day after. And there is a deployment phase that is foreseen in the coming months and years. So as I said, the idea is to address some of the limitations. So what you see here is a bit of that. This is a typical setup for a measurement device quantum key distribution system. And what you see, it's made of a laser, basically, an interferometer. Maybe not familiar with that kind of interferometer, but it's an interferometer. And then devices that are able to modulate both the amplitude of the light and the phase of the light. Okay, at the sender, that's it, and at the receiver, it's a bit more complicated. Okay, and it happens that these things that are fairly bulky systems, you can actually put them on a photonic chip. So that's exactly what we are going to do. We are going to make basically chip scale version of this so that they can be mass manufactured, that they have mechanical stability, so you don't need much more feedback or stabilization as otherwise, that it's small, etc. Yeah, that's good because in Belgium we are quite good at integrated photonics. That's work carried on at the University of Ghent and in the IMEC. We're also working on those what we call continuous variable quantum key distribution that with those squeeze states, and that's a work carried on at IMEC. We're also looking a bit forward at the quantum memories, and for that we are using atom-like systems that are called nitrogen vacancies in diamond. And this is work taking place in ASSELT and ULB. I'm going to skip over this. And then the security aspect, well, there are two things. One is to look at the whole system, as I already said. Another one is to improve the security of the authentication, because that's also one aspect that has to be dealt with. And currently, you basically have to trust the installer, the manufacturer, etc., because there's no really much more than that. For longer distance, I talked about post-quantum cryptography, and this work will be carried out by Kozik at the University of Leuven and the Royal Military Academy. And then there are also new quantum key distribution protocols. I already showed you a bit that the measurement device independent was in that sense a bit nice because you don't have to make assumption on the measurement device, but there are protocols that go even beyond that, that also take care of the receiver, and you can basically trust nearly no one and that still work, but that's work ongoing. And that's taking place at DOLB mostly. In terms of deployment, well, we'll put our hands on some commercial products, various kinds of commercial products. Actually, there's kind of a boom of commercial products that are coming thanks to this QCI initiative. And we'll try several of them at different places in Belgium. This is a work that is taken mostly in the hands of Belnet, just next door, but also with a partner that take care of the encryptor, Thales, the key management system. We have Multitel involved there, etc. We also want to go a bit beyond just two links. So we'll do what some people do from time to time, which is to have a trusted node. The solution that I told you was not very satisfactory. But fortunately, we have a Charlie that we can trust here because that will be Belnet. We'll have also, by the way, this is not completely trivial because it's basically making different quantum key distributions system talk to each other, and that's something that is not so common. We'll have also the measurement device independent QKD, and that's what we'll see in the second phase of development, where basically we'll have a loop around Brussels involving several quantum key distribution system, and then this measurement device independent system that allows different topologies that will be deployed hopefully around Redu. And in the last phase, we'll have those quantum links move around so that users can start playing with them. Okay? And the star shape of the MDI QKD will really look like a star at that point. And so as a conclusion, well, we are looking for users. So if you think that the quantum key distribution can be useful to you, please reach out. And with that, I want to thank people funding this, so Belspo and the EU, and the colleagues allowing this project to exist. Thank you.
Thank you very much. Are there questions on the presentation? I think I finally start understanding 2 or 3 things without doing the maths, but the logic. Il faut juste l'allumer en dessous. So thank you very much for the presentation. It's nice to see how it evolves. I think it's a big black box for a lot of people coming. You've addressed the part of the security and eventual vulnerabilities. I see it's work in progress. How do you see it evolve now with time when you look at timelines? And this is something that is coming. I don't know if the first computers are already working or about to work. I understood in Delft there's also a project on quantum computing that is pretty much on the way. What kind of timelines do you look at if I think